Hi everyone, in today's lesson we're going to talk about connecting differentiability and continuity. So we need another definition. A function is differentiable at x equals a if the function is continuous at x equals a and if the limits of the left and right hand derivatives are equal. So we know how to prove continuity, right? We could even write that here. So to prove continuity, we know that the limit as x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x, which must equal f of a. So all three conditions must be met in order for it to be continuous. Now we just have to add one more piece. In order for it to be differentiable, the limits of the left and right hand derivatives have to be equal. So the left hand derivative and the right hand derivative need to be equal. So notice the difference. This is f of x, which is your original function, and this is your derivative function. So I just want to show you a couple of examples of where the derivative exists. So here we obviously have a continuous function, right? There's no need to pick up the pencil, and there's no need for me to prove it algebraically. This is more of just an example about if the derivative exists. So at x equals 0, if I want to prove if the derivative exists, we're going to use the formula. And the formula is that the limit as x approaches a, but this time I care about 0, so the limit as x approaches 0 of f prime of x must equal the limit as x approaches 0 from the right. So we need a left and a right. Sorry about that. So the limit from the left must equal the limit from the right with the derivative. So we have this function y equals x squared. So we know that the derivative dy dx can be found by using the power rule. So 2x. So we can put in our derivative, or f prime, as 2x. And we want to take the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. So we're just going to do two small direct substitutions. So 2 times 0 is 0. 2 times 0 is 0. So the limit from the left of the derivative is equal to the limit from the right of the derivative. Therefore, this function is differentiable. Okay, same thing will work with this polynomial function here. That's a cubic function at x equals 2 this time I care about. So we want to take the limit as x approaches 2 from the left of the derivative, and we want to see if that's equal to the limit as x approaches 2 from the right of the derivative. So my derivative here, if this is f of x, my f prime of x can be found by using the power rule. So again, take the power, bring it in front. So negative 3x, drop the power. My plus 6x, drop the power. And the derivative of a constant is 0. So in for the derivatives, I'm just going to put negative 3x squared plus 6x. So negative 3x squared plus 6x. And we're going to take the limit as x approaches 2 from the left, and we're going to take the limit as x approaches 2 from the right. And as you can clearly see, if I do direct substitution and I plug 2 in, it's obviously going to be the same answer. So negative 3 times 2 squared plus 6 times 2. So 2 squared is 4. 4 times 3 is negative 12. Negative 12 plus 12 gives us 0. And this gives us 0, obviously, same thing. So the left and right hand sides are equal. Therefore, the derivative would exist at x equals 2. Now, it just happens to be a coincidence that these both are 0. It won't always happen like that. Okay, so now let's talk about a situation where the derivative fails to exist. So in a corner, like an absolute value graph, right? So we could call this graph y equals the absolute value of x. We have a corner, this sharp corner here, where these two branches of the technically piecewise function connect. It's not differentiable because the left and right hand derivatives will not be equal. It's almost like thinking about the slopes, right? Because we say derivative means slope. So the slope on this side is negative and the slope on this side is positive, so they won't be equal. Therefore, that's why the derivative fails to exist. Same thing about a cusp. we have it coming in and then coming in. Notice how it's kind of like curving and curving. This one's more straight lines. So same thing, these slopes of these lines are not going to be equal, therefore the derivative won't exist. A derivative won't exist at a vertical tangent. It's not differentiable there because it's technically undefined, right? There's your vertical tangent at x equals 0. And same thing at a discontinuity. We don't have a derivative at a discontinuity because it's not continuous, right? We said all the way back from the beginning, in order for a function to be differentiable, the function has to be first continuous. And if we look down here, their function is not continuous at x equals 1, right? There's a jump here. Therefore, it can't exist. Okay, let's do some more examples. So just to recap what we spoke about, differentiability must imply continuity, right? We just said if a function is differentiable, it has to be continuous first. But continuity doesn't always imply, I put continuity there, continuity doesn't always imply differentiability. So if a function is continuous at x equals a, the function is not necessarily differentiable at x equals a. And the best type of examples to use are piecewise functions. So we want to know, is f of x below differentiable at x equals 4? Well, we know in order to prove that it's differentiable, we have to see if it's continuous first, because it has to meet that condition. If it's continuous, then we can check for differentiability. So we know for continuity, we're going to check that the limit as x approaches negative 4, right, that's what they care about, of f of x from the left is equal to the limit as x approaches negative 4 from the right of f of x, which must equal f of negative 4. So remember these arrows, right? This is the left side, and this is the right side. So when I'm trying to find the limit as x approaches negative 4 from the left, I'm going to plug into this top here. So let me just first write down what the f of x is, x squared plus 16x plus 2. Bring down your limit as x approaches negative 4 from the left. Now go ahead and use direct substitution. Everywhere I see an x, put in a negative 4. Let's do this math real quick. So this is 16 minus 64 plus 2. Okay, and that answer is negative 46. And now we have to do the right side. So we want to do the limit as x approaches negative 4 from the right of f of x. So we'll use the right side, which is this one. So 8x minus 14. And we'll plug in negative 4 with direct substitution. Trust my math, you get negative 46. So the left and right hand limits are equal, and we know the value of the function will simply be the same where the line is. So this will be the 8x minus 14, so that'll work. So yes, it's continuous. So now we have to check for differentiability. So to check for differentiability, remember the formula is we need to take the limit as x approaches negative 4 from the left of f prime of x. And we want to see if that's equal to the limit as x approaches negative 4 from the right of f prime of x. So we have our left side and our right side, same in here, left and right. So left, we need to take the derivative. So we're going to use the power rule to take the derivative of this. So the derivative of x squared is 2x, the derivative of 16x is 16, and the derivative of a constant is 0. So I can write my derivative as 2x plus 16, and I want to take my limit as x approaches negative 4 from the left. So we're going to do direct sub, and we're going to plug in negative 4. So 2 times negative 4 plus 16, that's negative 8 plus 16 is 8. Okay, let's do the other side. We now need to do the limit as x approaches negative 4 from the right of the derivative on the right side. So the right side, here's this. The derivative of 8x minus 14 is simply 8. So we want to take the limit as x approaches negative 4 from the right of just 8. And the derivative, and the limit of a constant is simply a constant. So the limit of 8 is just 8. So the left and the right side are equal, Therefore, this is differentiable. So is the function differentiable? The answer is yes. Yes, the function is differentiable. Why? Because it's continuous and differentiable at the same time. Okay, so example number 2, same kind of concept. I'd actually love to see if you guys can do this problem on your own. So I'm going to say number 2 is homework, and you want to prove if the function is differentiable at x equals -9. So you need to first check for continuity and then check for differentiability. And we'll start class by going over this one tomorrow. All right, have a good night.